Hello viewers, welcome back to our YouTube channel, and today we want to continue with our series of quantitative techniques, and we have so far reached out to chapter 6 where we are dealing with measure of central tendency. In the previous video we gave an introduction to measure of central tendency or measure of location, and we had promised that we are going to look at each of the individual items that make up the measures of location. And in this video we are going to start off by looking at the arithmetic mean. We talk about the arithmetic mean. Of course, you can talk about it as arithmetic mean or just mean. Of course, the arithmetic mean or mean of a distribution of data, this is the sum of all the values, divided by the number of values in that distribution. So mean is a method of representing the whole data in a distribution by just one value. So it is one of the methods under the measures of central tendency that can help us to represent the whole data set that has been given to in that distribution by just one value or a single value, and we call that value at the central point or the average. Now, it is one of the most widely used measures of central tendency, and the challenge with it is that if you use a wrong average, you'll get inaccurate results. So the choice of the average depends upon the distribution of data and the purpose for which it is used to serve, or for the purpose of which we are going to use it. What are we going to, we are looking for the mean to do what? So arithmetic mean is a good measure, but cannot be effectively used when maybe the distribution has open-ended classes, when maybe some of the classes are too far away from the normal values. They may be high or they may be too low. Then the other thing is the fact that if the distribution is highly skewed, then we are going to find that mean will not be a good measure. Then of course the average is taken for, if it is taken for ratios or percentages, we find that it's not going to be an effective measure. So when you're looking at the mean, we said we can call it arithmetic mean or just mean. but it is the same as the arithmetic average or the mean, whereby we just found it by adding all the values of the data set and then we divide by the total number of values. So that's as far as the definition is concerned. And of course, if you want to maybe to specify and look at the properties of the mean, just because we looked at the general properties of the measures of central tendency, but mean, maybe to just give you a brief idea of the properties of the mean, is that it gives a general picture of the whole distribution. Because if you get the central point, then you can know on average such kind of data. You'll see that on average that kind of data that has been given to you ranges in such values. Then the other aspect is that it represents the entire distribution. In other words, it summarizes the whole data in the distribution, because when you are looking at the mean, we said you sum up all the values divided by the total number of values in that distribution. So it deals with the entire data set that has been given to you in the distribution. Then of course it can also be used for decision making, because as I told you, you can be looking at maybe the ages of students in a certain university, and maybe you want to find out what would be the average age of someone joining a university. Of course, you look at the ages of the different university students, then you get their average. From there you can be able to tell that within such a range we expect someone to be at the university level. So that's how we can use the mean or the average to make decisions. So those are part of the properties. But I want us to put our emphasis on the computation of the mean. Computation of the mean. Of course, we are going to look at the different methods that we can use to compute mean. Of course, if you are trying to find mean, we have said to find mean of a set of individual observations. Now we want to look at when we have what we call individual observations. These individual observations, when you just have the values, they have just given to you the individual values. So what you do, you add up all the values and then you divide it by the total number of the observations. If let's say the observations are maybe there may be 10. Of course, if you have been given the observations that, let's assume that these are the observations. This is x1, x2, x3, and maybe going up to xn. And our n is now going to be the number of observations. N is going to be the number of observations. And of course, our x will be the observations, the individual observations, or what we call the values. But these are individual values, they are not in a group. So for you to compute the mean, we've said that you divide all you sum up all the individual values and then you divide by the number. So we've seen the observations are x. Of course, we use x bar to represent the mean. Of course, we shall understand sometimes we give different symbols based on the fact that whether someone is looking at a population or they are looking at a sample. So we get the individual observation, which is x1 plus x2 plus x3, then plus up to we complete all the xn. Then we divide by the number of observation, that is n. That is the total number of observation. Of course, this can be represented as well as you can say, we can also say that mean is equal to the summation of x over n. Summation of x over n. And this n is actually the number of observation. Then summation x means the sum or the total values, or the total of all the values of x this is we divide by n, and we've said, of course, this letter here is a sigma, which represents the sum or the total of all values of x. So if you don't use this, you can use this, but most of the times they use this one. Most of the times they use that sigma x over n. So because we want to make sure that we don't look at this as a theoretical paper, we want to take a practical simulation, then we'll be able to do some computations, and then we see what we have. So let's look at an example, just a very basic example, for us to illustrate what we've talked about. Example, let's say determine the average. Determine the average height, using the data below. Of course, the data they have given to us, we have 171, comma, we have 180, comma, 154, comma, 160, comma, 155, comma, then 164. So they want us to get the average height of the data set that they have given to us. So we have seen the data set. Let's try to get the solution. Of course, we said that the mean is represented by x bar is equaling to the summation of x over n. So we are going to get the summation. We have seen that our n is equal to, there are 6 numbers. Then we need to get our summation x. And summation x is just for us to add up the 171 plus 180 plus 150 plus 160 plus 155, then finally plus 164. So we get the total of that. And then we divide by 6. I'm splitting this, but if you want, you can just take all of it at once. You can take all of this at once, whereby you can just say summation x over n, then you divide the whole of this by 6, whereby this total will be 984 divided by 6, giving us a 164. That is the average. They have not given us any units. They have not told us that this height maybe was measured in centimeters or was measured in foot. So we are not, if they are feet, they would have told us, but they have not given us any unit of measurement, so we leave it. But if they have given you the unit of measurement, you make sure you also indicate that maybe this is in centimeters, depending on what they have given to you in the question. So that's basically how we get the mean for individual values. And the individual values, they are the ones that we just add up. So for this one, you don't actually need to draw any table. You just add these values and then you get the mean. We will just say that the mean is just you sum up the values and then you divide by the total number of the you divide by the total number of you divide by the total number of the values or total number of observations. But maybe to clarify on this as well, on the symbol, because it may also, because I told you they can give you values, and these values they can be population. Population looks at the entire data set, but if it is a sample, then the letters keep on changing. So if we have a population, the values or the symbols that we use mu. can write it like that, mu, meaning it will be the summation of the x values, then divided by number of observation is taken as n, capital N. This means it is a population. But if they give you the question and it is a sample, for the sample we use the x bar, and this x bar is going to be the summation x divided by n, n is small n. The reason as why these formulas are the same, the only difference is that here we are dealing with a sample and here we are dealing with a population. When you are dealing with the population, number of observation are abbreviated as capital N because it includes the entire data that you have. So it will be, this capital N will be the total number of observations in the population. This small n will be the total number of observation in the sample. The reason as why we don't distinguish some of these things is that the at the end of the day, if you have been given a data set, the answer you are going to get here will be the answer that you will get here, unless the values they have given to you for computing a population are different from what they have given to you to compute a sample. That's when you have a different answer. So you take note of just that mere difference that you have to understand before we proceed, that when we are dealing with a sample, we use this x bar. But most of the times you'll find that in the questions, we always use this x bar, because the questions, most of the times they don't specify whether they are dealing with a population or they are dealing with a sample. That's why we find ourselves interchanging those values to whatever we want, especially the symbols. So that was just for individual values. Now I want us to look at still under individual values, but these individual values has what we call the frequency. So we want to look at those values that are going to be repeated several times, that you have been given the, yes, they are individual values or they are discrete values, but they have gone ahead to repeat some of those values several times. So we want to look at part B, where we have the mean of a discrete. Discrete means we are dealing with the individual values. When you have discrete frequency distributions, in other words, there is frequency. Of course, just to give maybe a small introduction, is that the values here, let me change the color. The values here, the values are first arranged. The values here are first arranged. When you are sorting out this, we first arrange, the values here are first arranged in a frequency, in the frequency distribution table. Distribution table, and then mean is calculated. The values here are first arranged into what we call the frequency distribution tables, and then the mean is calculated using a formula that is going to be including the frequency. So we've said that the values are first arranged in the frequency distribution tables, and then mean is computed. And then mean is calculated, and then mean is calculated. Now, the formula that we use here to compute the mean includes, it is summation fx over summation f. It is summation fx over summation f. Now, the summation f you are seeing here at the bottom as the denominator represents the total number of observations, and the summation fx here as the numerator on top represents the frequencies multiplied by the individual values, then we sum them up. But as I told you here, we first present, or we first arrange the data in what we call frequency distribution. So the way we do this is in a sense that we will find that the data set, the individual data values that have been given to us, are going to be very many. If let's say we are looking at maybe the number of the age for the different students in the entire university, you'll find that the whole university will be a population, but the people are going to be very many, and we are going to have very many students who are going to have almost the same age. You will find maybe those who are 19, they are in thousands, depending on the size of the university. So if that is the case, then we don't sum the individual values because the observations are going to be too long. And that doesn't necessarily mean that if you do it that way, you will get a wrong answer. No. But what we are trying to do is that we don't want to make computations very sophisticated or to be a very tedious work. That's why we use different methods depending on the data set that has been given to us. If you add them, you will still get the same answer, but you will take a lot of time. So what you do here is that you set these values and you assign them their respective frequencies. If one value, let's say someone aged 20, the people who are aged 20, they are maybe 30. Then you just write one figure 20 as the age or as the individual value, then you assign the frequency of 30. So the procedure of finding the mean for the data that has what you call frequencies, or in terms of the whether it's going to be grouped data or it's going to be ungrouped, we assume that the mean of all the raw data values in each of this class is going to be equivalent to that one value. Then with that one value, we assign the respective frequencies. So the mean we are trying to look at here, even though we are looking at individual values, these are ungrouped frequency distributions, whereby we have discrete values, but at the same time, these values are too many and they are repeating themselves. So let's have an example. Let's look at example 2. So this is basically for ungrouped data, or what we call the discrete frequency distributions. Find the arithmetic mean of the numbers. So they have given us the numbers. We have 10. Let's write these numbers: 10, 11, 12, 13, 11, 12, then 12, then 11, 12, 11, 13, 10, 11, 12, 12, 14, and then finally 11. So those are the values that have been given to us. If you count these values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There are 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the values that I have here, they are 18. Now you see that these values are going to be really very many. If you are to sum them, you will not find a book that will have a line that will accommodate or that will allow you to sum of those values. But even if you try to write very small letters, you'll find that the work is going to be very tedious. So the whole idea is for us to arrange the data first into what we call the frequency distributions. So what we are going to do is we are going to arrange this data into what we call the frequency distribution. So we have to first make a frequency distribution. So we have the values, and these values are actually our x values. Then we put the frequency. And then we are going, this frequency is going to be our f. So this is our f. Then we put the fx. It is f times x. That gives us fx. And we are done. That's the table that we want to draw. Now, if you look at these values, we have 10, we have 11, we have 12, we have 13, and then lastly 14. So the values are very few, but they repeat these values. You can see that we have a 10, we have a 10, 11, 12, 13, and then the 14 here. And these are the values that are repeating themselves. So what we do, we pick out those values 10, 11, 12, 13, and 14. Then the rest, we get their frequencies or the number of times they appear. So we write those as our values for x column. So here we have the first value we have is a 10, then 11, 12, 13, and then lastly 14. As our last value. Now we check on the frequency. We look at each of these values. How they are. We look at how these values are going to be represented. So here we shall have summation f, that is our frequency. Then here we shall have summation fx. Summation f, then summation fx. So let's go to our values. So we are looking at these values, and I'm going to be crossing some of them. We have a 10. 10 is there. That is the first 10. This is the second 10. So there are only 10 repeats itself twice. So it will be a 2. Then I go to another value. Another value that we have is 11. So I check 11 appears how many times. So I check 11. This is 11 for the first. This is first time. This is second, third, fourth, fifth, then sixth. So those are 6 times. It appears 6 times. So I come under our table, then I write a 6. I come here under 11. It appears 6 times. So this is going to be a 6. So I check on another value. I go to 12. I see 12. How many times does it appear? Now, once you have gotten these values, you can just multiply 10. This 10 times 2, you get the fx. So we check now the 12. 12 appears, select another color. So this is 1, 2, 3, 4, 5, 6, 7. It appears 7 times. It appears 7 times. So you go the other side, you indicate it. Let's move, and we indicate a 7 here. That this appears 7 times. Then we check 13. We check 13. 13 appears this is 1, 2. It appears twice. Then the 14, of course the 14 appears once. This is the only 14 that we have there. And you can see all the figures have been dealt with. So we move down here, we say 13 appears. 13 appears twice, and then 14 appears once. Then you sum these values here. You add up all these values. You add 2 plus 6, that's 8, plus 7, that is 15, plus 2, that is 17, then plus 1, that's 18. And when we counted those values, there were 18. So the one we have gotten here is 18. Then now we go on the side of getting the fx. We get 2 times, we get the frequency, frequency times the values. So we get 10 times 2, that gives you 20. Then 11 times 6, that gives you 66. Then 7 times 12, that gives you 84. Then 2 times 13, it gives you 26. And then 1 times 14, it gives you 14. Then you sum up all these values. You add these values. You add up the 14 plus 26, that gives you 40, plus 84, that gives you 124, plus 66, that gives you 190, plus 20, that gives you 210. So the 210 is the summation fx, the one we have put here, is 210. This is 210. So we can now conclude that our mean is actually summation fx over summation f. Of course, the other side we had written the formula, so you just come and feed in the values. 210 divided by 18. And once you do that, you get 11.66 6667. So you can put maybe to 3 decimal places. And that will be your mean. If they had not given us the measurement, so we leave it without anything. So that would be the answer. So that's how we get the mean. We calculate the mean by first presenting the data set into what we call the frequency distributions. So those data set can as well be examined when they have given to you what you call when they have given to you the table. Let me just show you how they can present it in a table. Then we move to the other method of computing, still the mean. So let's look at example 2. Example 2, the number of children who go to school per family on a housing estate were recorded as follows. So let's have a table. So let's have the table that shows the number of children and then the number of families. Number of children, then the number of families. So the main subject, we are looking at the number of students. So we are focusing on students. It is the families that are going to work as frequencies. So we have 0, 1, 2, 3, and then 4. We are looking at the number of students who go to school. Those that don't go to school in different families, the families are 12. The implication is that 12 families, they don't have anyone who goes to school. They don't have a child that goes to school. Then there are 15 families which have one student or one child going to school. Here they are 5, here they are 2, and this one they are 1. So this last one means that there is only one family where where four children go to school. So they are telling us find the mean number of children per family who go to school. So this question is all about students, those who go to school in a given estate. They look at a given housing estate, then they ask. So if you try to look at this, it means you should be able to interpret this, because here they just don't want you to find the mean. They are telling you find the mean number of children per family who go to school. So you have to, once you are done with the computation, you go ahead and conclude or explain what you have got. Of course, you say that on average, maybe one or two or three children per family. But of course, you can see that if you look at this data set, the moment you keep on looking at this data set, you'll understand that you can see that most of the families, almost 15 families, have at least one person going to school. You look at this one, the one who don't have, vis-a-vis those who have. If I'm to just explain to you this data set, just from a table representation, you can see that at least the maximum families, at least 15 families have a kid that goes to school. You can see from here, because the frequency here is so much, as opposed to, you can see that it is decreasing. This one is 5, this is 2. As the number of kids increases, it means that if I'm to make a decision on the housing plan for the next estate, I know that I will be knowing that most of the families have, let's say, one kid. Because if you look at the 12 families that don't have any kid that goes to school, meaning all of them, maybe they are still having young people. Even when I'm setting the rooms in that kind of area, I know that these people I'm building these houses for, they don't actually have many kids. You can see that the person who has maybe 4. So that's the kind of analysis. That's what basically we were trying to talk about as regards to table representation of data. So if I had highlighted all these values 0, 1, 1, 1, 1 15 times, it will be a lot. I hope you are getting the reason as to why it's not all about finding the right answer. It's all about how you can simplify the answer. Because we still get the same answer, but the implication is that we want to simplify the work. So let's solve this. Solution. We said we are going to use number of children. Maybe you can just use children. These are our x. Then the number of families, we can just use maybe families. These are going to be our frequency. Then summation fx. Of course, we get the f times the x to give us fx. Then we go ahead to put in the values. We start from 0, 1, 2, 3, up to 4. Then the frequencies, of course, they have given to us the frequencies This one is 12, this is 15, this is 5, this is 2, and this is 1. So we sum up this column, and then we multiply this times this, and then we sum up the products. So we get this 0 times 12, that will give you a 0. 0 times 12, that gives you a 0. Then 1 times 15, that gives you a 15. Then 2 times 5, that will give you a 10. And then 3 times 2, that gives you a 6. And then 4 times 1 gives you a 4. So you add 0 plus 15 plus 10 plus 6 plus 4. Then you also add 12 plus 15 plus 5 plus 2 plus 1. So this we have the summation f, which is 35, and we have the summation fx, which is also 35. So we get our mean, which is summation fx over summation f, and this is 35 over 35. That gives you a 1. Now, how do we conclude? What is the interpretation of this? The interpretation is that on average, one kid or one child goes to school per family. And that's what I had explained to you earlier. That's why under the properties, we said that we always have that value that we said whenever we look at the mode is always seen as a critical value. Why? Because at some point it can be the deciding factor when you are making a decision. So we have seen that one kid add a frequency of 15. And if you are to look at the mode, that would be our model value would be 1, because this it's all about the number that has the highest frequency. And you have seen even when we computed the value, we found that actually even the mean was 1. So this means you can conclude and say that this means on average, or at least one kid, one child goes to school per family. So if you have been given the assignment to carry out the computation and then you come up with a conclusion, you'll find that the conclusion will actually make sense. Now, I want us to look at situations where we have what we call the assumed mean. Specifically, when we are dealing with data values that is not grouped. This is still under the ungrouped, or what you call the discrete. It is still under the discrete frequency distribution. So we want to look at a situation where they want us to calculate mean. Maybe this is part C, calculation of mean. Using, sometimes they call it a working mean. Working mean or assumed mean. Just like the way the word suggests, assumed. Someone can assume that on average, I have, let's say, 20 people in the factory. So you start with the average that you have to find out whether this person actually gave a right mean. Because someone can ask you, how many people do you employ roughly on average? How many people do you employ in your factory? And you can say maybe on average they are 10. But the big question is, are they 10? Of course, they may not be 10. So the implication is that calculate the actual mean, but you base on assumption that the mean was assumed to be 10. So that's what we are going to compute. If, let's say, in the previous question, they had told us that maybe on average, one person goes to school. They start from this conclusion that we have just made here. They say on average, one person goes to school. Then they tell you to calculate the mean. So that's basically what we are going to look at. Of course, now to give a small background is that in this method, we do what you call deviation. We get something that is called deviation. Deviation, denoted as small d. Now, the deviation is like the difference or the change. It could be a negative, it could be a positive change. The deviation of each variable. We get the deviation of each variable from the assumed mean. Deviation d of each variable from the assumed mean should be calculated or found. And how do we get that? We said for us to get that, it's just a matter of, it's a deviation from the assumed mean. So this d is actually going to be equaling to the value that we are taking off. Maybe it is x minus the assumed mean. Let me just call it am, assumed mean. So our d will be the difference of that variable, which is the value, minus the assumed mean. So we get the change, because for you are assuming that the mean is 10. So we are getting each of the individual values, we subtract 10 and we see what is left there. So the deviation is very important. The deviation has to be computed, and any value among or outside the distribution can be taken as the assumed mean, because in some questions they may not tell you the assumed mean, but they will tell you to use assumed mean, meaning you will assume your own value. It can be among the values or it can be outside the values. So that's the other argument that I told you, that they may tell you, they may ask you maybe how many employees do you have, and you say roughly around maybe 20 people. But these 20 people, you may actually find that you have maybe 10 people. But for you, you said 20. You see that the 20 is far away from the rightful average. Or it may be, you may say you have 20, but when you compute the actual average, you find that it is 50. On average, you have 50 employees, but for you, we are saying 20. So that's why we are saying that the assumed mean can be part of the x values, or it can be outside the x values. It can be among the distribution, or it can be outside the distribution. But now the deviations that we have computed, this d is going to be multiplied by the frequency, the corresponding frequency. And once you have multiplied the deviation d with the corresponding frequency f, you'll get what we call fd. Once you get the fd, you calculate the summation fd, and the formula will be the assumed mean that we have plus summation fd over summation f. So you will understand some of these things when you go to when we pick a practical question, because you'll find that this d at some point it might be a negative or it can be a positive, because I may take an assumed mean that is higher than the x value. You'll find that the result will be a negative. So at some point when I'm adding, for us we are saying we are adding, but you will be adding, but at some time you will be subtracting, because there you will be, once you add a positive plus a negative, of course it will be like a subtraction, because a positive times a negative, you get a negative. So either way, we shall be able to to get this. So even if you have gotten a negative or you have gotten a positive, you don't need to worry. Just continue and do the computations. So when we are using the assumed mean method, how do we compute the mean? So let's write the formula very well. The mean, using assumed mean method, the mean will be equaling to that assumed mean, which I'm calling A, plus the summation FD over summation F. The summation F is total frequency. Summation F, let me also explain where summation F is actually the total frequency. Then our D is now the deviation. That the D is the deviations that we have computed. We said D represents where D is the deviations from the assumed mean. And our D, we said, is equivalent to X minus the assumed mean. And of course, FD is just the product. So let's look at a simulation. We get an example and then we try to solve and see what we can have. So the question says the following table shows the average saving contribution contribution per worker per month. Per month in thousands. They are in thousands of shillings. In a savings scheme. In a savings scheme. Of course, we have the savings. We have the savings in thousands of UJEX. Then we have the number of persons or workers. So we have the first one as 5,000. It is 500. The second one is 600, 700, 800, 900, 1,000, and then 1,100. So the frequency, this is 1, 3, 5, 7, 6, 2, and 1. The required says calculate the arithmetic mean. Calculate the arithmetic mean. Calculate the arithmetic mean savings. They want us to calculate the arithmetic mean saving for the workers using the assumed mean method. Calculate the arithmetic mean saving for the workers using assumed mean method. Using assumed mean method. Now you can see that in this question they have not specified for us the assumed mean that we are going to use. So it is our duty to pick any assumed mean. It can be either within the data set or it can be outside the data set. So the first thing you start with is for you to, of course, if you look at the solution, the first thing you start with is to estimate the assumed mean. So I'm going to say using 800 as assumed mean. Don't forget the fact that these values were in thousands. I'm just picking 800, but it means it is 800,000. Assume we are picking 800 as the assumed mean. So we calculate the mean saving. The mean savings as per as below. So we have to display this data set in a frequency distribution table. So go ahead to draw a frequency distribution table. So we represent the x values. We have the x and then the frequency. Then we show the difference, that d, which is actually x minus 800. Then we indicate the fd, that is f times d. So the first one was 500 with the frequency of 1. The second one is 600, 700, 800, 900, 1000, then 1100. You can see that the 800 figure that I picked was within. But even if you pick a figure that is outside, it is okay. 3, this is 5, 7, 6, 2, and 1. That's the frequency. Of course, now you get the summation f. That is the total frequency. But let's first compute these values. So we are going to get the d. Our d value is going to be the 500 minus 800. That will give you negative 300. Then we get 500. We get now this x. This it was x minus d, which is 800. Now we are going to 600. It is 600 minus 800. That gives you a negative 200. Then we go to the next x value, which is 700. 700 minus the 800. That gives you a negative 100. Then the next x value is 800 minus 800. That gives you a 0. Then we go to 900 minus 800. That gives you a positive 100. Then 1000 minus 800. That gives you a positive 200. Then 1100 minus 800. That gives you a positive 300. Then you multiply. We are multiplying this frequency with the d. So we get 3. We get 1 times the 300, the negative 300. That will give you a negative 300. Maybe I change the colors. It is a 3 times negative 200. That gives you a negative 600. Then 5 times negative 100. It gives you a negative 500. Then 7 times 0, it gives us a 0. Then 6 times 100, it gives us positive 600. Then 2 times 200, it gives us positive 400. Then 1 times 300, it gives us a positive 300. Then we go ahead to add up this column. So we add up this column and then this column of the frequency. So we sum up these values. We sum up these values for the frequency. And then we also sum up these values for, so this is summation F, and our summation F is 25. Then we also sum up summation FD, which is negative 100. Then we get the mean. Our mean, can use X bar, is equivalent to 800, which is the assumed mean, plus the summation FD, which is negative 100 over 25. And once you sort that out, you'll find that you have 796. Because this is a negative, meaning it will reduce this figure. So for us, we assumed that our, but remember these values were in thousands, so we multiply by 1,000 to give you the money, the monetary value, which is 796,000. That is the money, the monetary value. So for us, we assumed the assumed mean was 800. The mean saving was 800. Yet in actual sense, the actual mean was 796,000. So we had overstated our average saving. Now, I want us to look at one last portion in regards to ungrouped frequency distribution as far as mean is concerned. I want us to compute one last item to do with the mean, and then we shall look at the mean for grouped data or grouped frequency distribution. But before we look at the grouped frequency distribution, there are also scenarios that may arise that may be the assumed mean that we had taken was maybe too small, and we ended up having very high values of the deviation D. Because the reason why we use the assumed mean is to make sure that we simplify the computations so that we have reasonable figures. Now, what if the values were in billions and we are depict maybe the assumed mean to be around 1 million, and we found that the D that we have gotten, or the difference that we have gotten from subtracting the assumed mean from the individual values is still very high. What do we do? Because the reason as why we are using all this method is not because we want to get the right answer, but we want to simplify the work depending on the data set that has been given to us. So if you find that the data set they have given to you, you tried to reduce it with unestimated assumed mean, because we said it can be within or outside. We can pick any value because we may not even know, we just assume. But what if what we have assumed is small and we ended up having a higher deviation D? What should we do to simplify the work? We introduce another method called a step deviation, or what we call the coding method. So we are going to look at the coding method as one of the ways of computing the mean. So we are looking at the other option called step deviation. Step deviation in bracket coding method for mean or arithmetic mean. So when the values, of course, let me write something just to create some, when values obtained from deviation, when values obtained from deviations from the assumed mean, are still from the assumed mean are still large or are still large numbers. Are still large numbers. When they are still large numbers, full stop, you may use a step deviation method. Use a step deviation method which is which is a modified or which is a modification from assumed mean method. So this step deviation or coding method is just a modification of the assumed mean. So we still use the same principles of the assumed mean, whereby we assume a given mean, but when we find these data values are actually higher, or they are still very high values, then we end up with a different approach. But still, we will be getting the same answer. So what am I going to do? I'm going to use the same question that we have just finished. Then I assign this method to make sure that we find the mean, and the mean has to be the same. So that's what I want us to look at. We want to confirm whether we are actually going to get the same result. Because as I said, this is just a modification, or it is an improvement of the assumed mean, given the fact that the assumed mean may have a deviation d, or the different deviations may be still large numbers that we need to simplify. So the formula for computing the mean is just the assumed mean plus summation. I'm just going to use a different letter. Let me say summation fu over summation f times h. Now, where the letter u represents d over h, and h is, this h is a common factor, of d. And remember, our d is given by x minus the assumed mean. So this is the formula that I want us to use, so that we can be able to prove that we can actually use this, then we get the same answer. So you have gotten this letter u, this one here, represents d over h, and our h is a common factor of d. So we are still going to use the same question that we have used to get the assumed mean. Then we want to make sure that we use this method and we'll be able to get the same result. So we are going to draw this same table as it reflects here. Then we are going to pick our common factor. The common factor, if you look at this question, you will see that the question factor within our D here, the common factor is 100. There is 100 this side, it's a negative 100, and this side there is. So we can take 100, we can take 200 because there is 200 this side and there is 200 this side. We just pick a common value as long as it has both negative and a positive. So this, we are going to draw this same graph from here up to here, up to this D. Then we proceed with the rest of the steps for us to use the other method. So the same answer that we got, which is 7,900, it's 796,000. So we use the same question. So let's organize the table. We have the X values. The first one was 500. The second one was 600. This is 700, 800, 900, 1,000, then 1,010. So for the frequency we had 1, 3, 5, 7, 6, 2, and then 1. Then our D, we assumed that it's going to be X minus 800. We took 800 as our assumed mean in the previous question. So we are maintaining that. So we know how to get the D. So this was negative 300. This is negative 200. This is negative 100, 0, 100, 200, and then the 300. You can see that these values are still high. They are still high values. They are in 200,000 because remember these values were in thousands. Now we have reached this spot, this side, and we said that we are going to focus on getting the U, and we said our U is D over H, and we assumed that our H is equivalent to 100. We picked 100 as our H. Then we get the FU, F times U. So we go ahead and multiply. We multiply F times U, the U that we are computing here. So let's first get our U. To get our U, we said we get D, which is 300 divided by 100. That is going to give you negative 3. This is 200 over 100. It is going to give you negative 2. This will give you negative 1. This will be a 0, and then this will be a 1, this will be a 2, and a 3. Then when you multiply 3 times 1, negative 3 times 1, it is going to give you negative 3. You multiply this times the frequency. Then 3 negative 2 times 3, it is going to give you negative 6. And this one is negative 5. This is 0. This is 6, 4, and then lastly 3. So we sum up this frequency and then this FU. So this F, this H, it's you to pick it. If you pick 100, let it be 100 for all. That's why we are saying a common factor. It's going to be one value, but it is reflecting all the values. It is working on all the values to get our U. So you can see that this is 3 and 300. So this is just 3000, negative 3000, and this one is negative 300. So we get now these values. We get the summation F. The summation F here is 25. Then the summation FU is equaling to negative 1. So we substitute into our formula, which was x bar equaling to assumed mean plus summation FU over summation F times H. So we can see that this is going to be equivalent to 800 plus, it is 800 plus summation FU, which is a negative 1, divided by 25 times 100. The 100 is the H that we chose. Of course, you can see if you work it out, you will find that it is going to be negative This is going to be negative 100 over 25. That gives you a 4. A negative 4. Of course, negative 4 minus 800 and 800, it gives you 796 times the 1000, because these values were given to us in thousands. That will give you 796,000 Ugandan shillings. So this gives us UJEX 796,000 as our answer, which is the same as what they had given to us in the question. Now, that's all that we wanted to talk about as far as the mean for ungrouped data is concerned. Now I want to look at the mean for grouped distributions. We want to look at mean for grouped distributions. We want to know how can we be able to calculate the mean for grouped distributions, because sometimes a distribution is going to be very large, very large, and it varies. So if you find that the distribution is very large and some of the items are repeating themselves, we will find that it is going to be cumbersome for us to work around the original raw data. So we will find ourselves being forced to group into what we call classes. We shall have to group the data into what we call classes. Now, when we are grouping the data into what we call classes, we have to have something that is going to change. Something small is going to happen. In that, when we have classes, we no longer have individual X values. So the only thing that is going to change is, for us, how do we compute the X values? Because we are going to have classes that are going to be in intervals. So what we need to know how do we get the midpoints, and we talked about how to get the midpoints depending on the data set that has been given to you. If they give you class boundaries, you add them and then you divide by 2. If they give you class limits, you add them, divide by 2. Those are the midpoints. So these midpoints, they are the ones that are going to work as X values. The rest will be the same. The moment you get the midpoints or you get the X values, you do the same thing that we have been doing using all the methods that we have talked about. So that's the only thing that is going to change. So the procedure for finding the mean for the grouped data, we always assume that the mean of all the raw data values in each of the classes is going to be equaling to the midpoint of that class. Maybe let me write this because it is very important that the procedure for finding the mean for grouped data assumes that the mean or the average of all the mean of all the raw data values in each class is equal to the midpoint of the class. Of course, we know that in reality this is not true, but it's an assumption. It's not true. Let me give you a scenario. If I have a class of 20 to 30, a class of 20 to 30, it's not true that it's average. The average values that are within here are actually 20 plus 30 divided by 2, which gives you a 25. The average is not 25. Because from 20 to 30, we have very many values. We have 20.1, 20.00001. There are very many values that are within this range. So for us, we just assume that the average, let the average of all the values that are within this range be equaling to the summation of the lower class limit and then the upper class limit divided by 2. That's the midpoint. But it is not always true that the midpoint is actually. Now, what if the data set that was given to us was just maybe 20.1 up to 20 maybe 19. How are you going to tell me that the average is 25? So in reality, it's not always true, but that's the assumption, because we assume that the average of the raw data values in each of the classes, we assume it will always be equaling to the midpoint, but it's not true in reality. However, if you are using this procedure, we have some approximations of the mean, since some of the values may fall above the midpoint, others may fall below the midpoints for each of the classes, and the midpoints may represent an estimate of all values in the class. So this 25 that we have gotten here, the 25 that we have gotten here is a representative, is assumed to be the representative value for all the values that belong to that class. But we may find that we have values that are maybe 29, which are above the average. And we may find that we have values that are below 25, maybe they are 21. That's the implication that we are trying to make. So we make, it's an approximation. We approximate that the average number of the values that are within a certain class, let it be the midpoint of the two values. That is the upper limit and then the lower limit. So you need to know how to deal with values when they are in classes. It is very important because we may have data that is going to be spread in each of the different groups, and it's impossible to determine the mean when the values are spread. So that's why what we find out, what we try to compute is an approximation to the mean. So it is assumed that each of the values within a class interval is equal to the midpoint at that group or at that class. But the other key thing that we need to note is the fact that the class interval are always going to be assumed to have the same size. So if from one class to another class we are skipping 10, we should be skipping 10 throughout. That's the other assumption. So there are usually two types of class intervals. We have the ones for continuous and then the discrete intervals. Of course, a continuous interval leaves no gap. The continuous interval is the one with the other classes, because you know the types of classes that we looked at. If we are moving the exclusive classes, they are the ones which have the continuous intervals, because for them they leave no gap between the class intervals. You may have maybe 5 to 10, 10 to 15, 15 to 20. Those are the ones we call the exclusive classes. They are the ones that have what we call the continuous intervals. For them, they leave no gap between the class intervals. Then the discrete intervals, they are the ones that take the other inclusive classes of 4 to 9, 10 to 14, 15 to 19, and so on. So, which formula are we using here? We are using the same formula. We can use any of the formulas that we have looked at. The whole bottom line is for us to be able to get the midpoint, and that midpoint will represent our x values. So our mean will be summation fx over summation f. Or you can use assumed mean any of those, as long as that you know that this x here represents x equal to the midpoints of each class. Then we multiply each class's frequency to be able to get that. So we need to maybe compute one example using one of the methods, then the rest will be for you to go through the different questions and be able to take out some simulations. So let's look at the simulation and then we finalize this. Says given the frequency distribution below, we have now the frequency distribution where we have the values. We have 71 to 75, we have 76 to 80, we have 81 to 85, then of course we also have the frequency here. This is 1, 2, 4. So this we have 86, this is 86 to 90, and then have 91 to 95. 91 to 95 with a frequency of 4 and 5. Then they also give us the total frequency here. They give us the total frequency. The total frequency has 16. And the required, of course, they want us to compute. They want us to find the arithmetic mean of the grouped frequency distribution. The required is for us to find the arithmetic mean of the grouped frequency distribution. So that's what we are going to compute. And of course, the first thing that we need to do is to make sure that we find the class midpoints or mid values of each of the classes that have been given to us. And once we have gotten the midpoints, then you go ahead to compute the mean using those midpoints as our x values, and sometimes they call them class marks. So as long as you have gotten the midpoints, you go ahead to do what we have been doing in the other aspects. So the only thing that is going to change whether they have given to you which classes are the fact that you need to get the midpoints, and these midpoints are the ones that are going to work as our x values. So we put in the values, and of course we have the classes. We have the classes. We have the classes, and the classes are 71 to 75. 71 to 75. We have 76 to 80. We have 81 to 85. We have 86 to 90, and then lastly we have 91 to 95. Of course, the frequencies, we have 1, 2, 4, 4, and then lastly we have 5. So we compute our fx. Of course, this is our x value. No, these are our classes. We are now computing our x values, which are the midpoints. So we have said you get 71 plus 75 divided by 2. This will be 73. This is 78. This is 83. This is 88. And lastly, we have 93. So you multiply this times this. 1 times 73, it will give you 73. And then 2 times 78, it gives you 156. This will be 332, and then 3. This one will be 352, which is 4 times 88, then 5 times 93, giving you 460. Then you come here and sum up this fx and this f. Of course, they had given us the summation f, which is 16. Then we get so this was the last class was 91 to 95. This was 5. This was 93. And then this was 465. Then we sum up these values. The summation f was given to us. Summation f, we had it as 16. This was 16. Then this summation fx is actually 1376, the summation fx. So we get this 1376. We get this 1376 divided by 16, and then we get 86.125. So we get the mean. We get our mean, and mean is going to be summation fx over summation f, and this is 1776 divided by 16. That gives you 86.12 as our mean. .125. This is our mean. So you can go ahead to use step coding or step deviation to get the mean, and then you'll be able to get the same answer. So whichever method you try to use, you will still get the same result. So thank you for watching. That's all for the mean. We shall go into the next video as we are looking at the median.